For those of you who remember, you spent 6 months in high school learning how to balance redox reactions. And just put protons and hydroxides on everything and keep it all neutral, and it does it automatically. You don't have to worry about oxidation states and all the rest of it. That's why I've got sulfuric acid going to hydrogen. It drives the chemist crazy, but of course there isn't any sulfuric acid in the water. But in fact, if you want to do stoichiometry, that's how you do it. And so you can see that it takes 2 moles of organic carbon to reduce a mole of sulfate to a mole of sulfide. And then you have the precipitation of hydrogen sulfide to make McEnroe, and we didn't want to and have still not built reasonable chemistry into these models. We did some phosphorus work, as I remember, but anyway, so the precipitation, when you exceed the solubility of hydrogen sulfide, depending on what the iron concentration is, you make McEnroe. So this is solid iron sulfide. So what happens is you can diffuse hydrogen sulfide up and oxidize it. But if you make a lot of this, the particle mixing brings it up, and you can oxidize that. Okay? So there are 2 reduced substances that you have to worry about. One is the dissolved sulfate itself, and the other is the particulate iron. Okay? You can bury particulate iron. The magnitudes of both of these up here depends on the magnitude of particle mixing relative to diffusion. Iron sulfide oxidizes very rapidly. This is, it's also called acid volatile sulfide because of the way it's measured. You acidify the sample and you just see how much sulfide comes off. And so you can see that it reacts very rapidly, hours. And the oxidation rate is linear to oxygen. So we build that into the kinetics. So the partition coefficients are, unfortunately, parameters in the model. They are not chemical specific. If we built a model where the chemistry was done properly, we could actually calculate it from the solubilities and all the rest of it. But at this stage of the game, we decided let's just put in some numbers. So to show you how it works, this is the fraction of diagenesis, carbon diagenesis. So how much organic matter is being mineralized and where does it all go? If the partition coefficient is very low between the solid iron sulfide and the hydrogen sulfide, about 60% comes out as SOD and 40% comes out as hydrogen sulfide flux. If, on the other hand, the partition coefficient is very large, it all gets buried. I forget what these are for. Oh, this is the oxygen. This is what happens in the overlying oxygen. If the overlying oxygen concentration is negligible, then most of it comes out as a hydrogen sulfide flux, and a little bit gets buried. But once you get overlying water oxygen, you get all just SOD. All right? But you can see down at 1s and 2s, you're pumping out a fair amount of SOD, which is why the Chesapeake Bay model has reduced substances in it. The sediment flux model is pumping out essentially hydrogen sulfide, or it's oxygen equivalents of oxidizable stuff, of sulfide oxidizable material. Particulate mixing is important in this model, as I think I've pointed out to you. It's what keeps phosphorus buried. It's what mixes iron sulfide into the aerobic layer. And so we built a model where we were worried about how organism density varies over time. So this is, I forget what station it is. But anyway, these are annual cycles, 84, 85, 86, and so on. And this is the DO at the bottom, up, down, up, down. And you see the oxygen gets to nothing. And you see the organisms recover, and then they're knocked out, and then they start to grow, and then they get knocked out. And if it's not too bad, they grow high, and then they get knocked out. So we've built a little simulation that does that. It basically cycles the benthic mixing. So if you get a strong anaerobic behavior, it pretty well just kills them off. And then they start up fresh the next year.
So they respond very quickly.
Yeah. Well, they don't, oxygen, you know, they're obligate aerobes. A couple of hours, they're dead. And here's some more data. You see, it doesn't get quite to zero, and so you see the organisms growing way up there. So we have a little model in there that is tracking the overlying water oxygen and trying to reproduce this kind of stuff. It's pretty rough. All right. Once you run out of sulfate as the oxygen acceptor, electron acceptor, then the last thing that's left is you can make methane. So you need a methane model. What's interesting about methane is that the model looks just like, you know, again, you generate methane because you've run out of sulfate. You get a diffusion coefficient, a surface mass transfer coefficient, and you get it up in the aerobic layer where it oxidizes. Some of it oxidizes, some of it escapes, depending on the situation. But what can happen in the anaerobic layer is you can make enough methane so that you then get saturation and you start to form bubbles. So methane gas will pour out of sediments. So you got to deal with that problem as well. So that's why this is curving over. We had an experiment done. This was done for a problem we worked on in Milwaukee, on the Milwaukee River, and we were concerned about. So there wasn't any sulfate, so the only place, there wasn't a lot. So the only place the material could go was either use up oxygen or generate methane. And they were putting in a very large sewage interceptor for combined sewer overflows. And what they were hoping was that the SOD would get reduced a lot. And then when we started to realize that you had this problem, they may have ended up just reducing the methane flux and having done nothing or not a lot to SOD. That was a grim year or two before we figured out that it would actually work okay. You see, because half of this stuff, this is all methane coming out. That difference, what else could it be? If there isn't any iron, there isn't any sulfate, you're generating methane.
Just as a point of interest on the Conowingo, it's a hydro station.
Right.
And when Jeff was out doing some flux measurements, when they would release water to generate the power, the water levels would go down and they'd see the methane escape.
Sure.
Over a couple hour period.
Yeah, absolutely. The pressure drops, the solubility goes down, up, down, and so you're supersaturated and out comes methane. One of the young professors showed me a little trick. They go out into a marsh, they put a little tube, and they light it. And you can see little flames coming out. Anyway. It's interesting, we actually, in the sediment dilution experiment, which we had done, you can measure the gas flux, and we were measuring the SOD, and you can see the relationship. This is what the model is doing. See, there's no gas flux being generated, then all of a sudden the gas flux starts to generate.
Back to the
Sure.
previous slide. I'm looking at that and wait.
Oh, you don't understand it? Sorry.
So
Let me describe it. This is a dilution experiment. We took the sediment and diluted it with sand, and then incubated it aerobically. So aerobic sediment overlying water, and then put a gas trap on top of it. So it's Mortimer, but it's sediment.
I see. So it's the same sand, and the SOD, you would expect the concentration to be linear.
Right, if there's no other way of, right, if nothing else was consuming carbon diagenesis, it should be linear. But it ain't, because some of it's escaping as methane.
As methane, so the deviation below the line is methane that's escaping.
The deviation between the linear and that line is methane.
Right.
This is the amount that's oxidized. Way down low, it's linear. You haven't exceeded the solubility of methane yet. So then all of the organic decomposition is oxygen as the electron acceptor.
Is going to methane.
No, it's going to it's being consumed. So way down here, see this little linear piece? That's exact. It's flat because as you double the amount of sediment that you have, you double the SOD. But as I continue to double the amount of sediment, then suddenly I exceed the methane concentration gets too large.
And the methane goes away.
Correct. This thing gets too large and you make bubbles.
Now I understand.
Okay? All right, so if you think about it, you've got to build a model that can handle the aerobic layer. If you build a multi-layer model, the Dutch built a model that looks like this. You have the layer in which denitrification is occurring, you have the layer in which sulfate reduction is occurring, and then you have the layer in which methane is being produced, if it actually is being produced. And so you got to solve equations for the depths of all these layers, which is a real pain in the neck. So what we did instead was to just take a two-layered model and calculate what these depths had to be, and then just proportioned the diagenesis to each of those reaction sequences. So depending on what the concentration is, how much sulfate you have, this may be 0, in which case you're not making any methane at all. If there isn't a whole lot of sulfate in a freshwater system, then it goes to methane right away once you've used up all the nitrate. So this is how the model is actually structured. It calculates those layer depths.
And to make the one on the left even more complicated, is those layers would be changing dynamically as well.
Correct. Entrainment, exactly. Real headache. Real pain in the neck. Don't want to do that. We actually had to correct for the entrainment of the aerobic layer. Remember? Mm-hmm. That was a headache. Where'd my, am I being shut off? Oh no, here it is. Anyway. So here are some examples of just computations. This is to give you a feel for where the carbon diagenesis is going. So there are only 4 places it can go. It can either come out as an aqueous hydrogen sulfide plus methane flux. That's the dissolved COD coming out of the bottom for the water quality model. It can be exerted as SOD. It can be a gaseous flux of methane as bubbles, and it can also be buried. I don't know why I don't have burial in here. And you can see what happens depending on what the overlying water sulfate concentration does. So methane gas is what you want to concentrate on. You can see as the sulfate gets higher and higher, at seawater kinds of concentrations, you have to go to very high carbon diagenesis, 10 grams of oxygen per meter squared per day. Whereas if there's only a little bit of sulfate, you get methane right away. You don't really get much of a, these are log scales, you don't really get much of a dissolved flux. It's mostly either SOD or methane fluxes. On the other hand, if you have a very, so this is SOD over DO, so there's a very, very narrow layer. Now you're getting lots of escaping, very little oxidation. So you're getting hardly any SOD. It's all escaping as either dissolved intermediates or, right? That's when the aerobic layer is shrinking down to nothing. There's no oxygen anymore, everything's pouring out. So you can run calculations like this with the model just to give yourself a feel for how it all works. Here's some real data that we did on the Chesapeake Bay where they actually measured some methane gas and SOD, and the comparisons are model and data. It really works okay. It's log scales, of course. What I want to show you. Yes.
Just a quick question for Carl. The methane gas, do you end up keeping that, assuming that the gas dissolves in the overlying water column, so it ends up as aqueous SOD, or does that lose from the water column? I don't know if you know, but
no, but I know. I just consider it's inert.
It's inert. Okay, so it escapes.
Yeah.
Okay.
Oh, really? You don't oxidize the methane? No. Okay. Well, it's not going to matter.
The dissolved methane, you oxidize it.
Oh, the bubbles go away.
The bubbles go away. Okay.
Okay.
No, actually, for the sake of whatever, I let the dissolved stuff go too. I looked up methane oxidation rate.
They're fast
in water, and it ain't much. You know what I mean? Oh
no. Well, we looked at that. It's not going to make any difference. You're not getting any methane. You got so much sulfate in the marine water.
Well, except in the freshwater portion.
Yeah, you should look. It is oxidizable. There's a fair amount of data on that. Now, here's something go ahead.
Well, one more diversion.
No, please.
It caused me a great deal of headache.
Oh, really?
Well, here's the problem. If you had that methane be transferred, this is a practical problem.
Yeah.
From the freshwater part of the Potomac River to the saltwater part of the Potomac River. In the saltwater part, I have the decay rate of reduced material is great because it's sulfide.
Oh, okay.
In the freshwater part, it was relatively low, but it was some small.
Yeah, but it's not like sulfide. Sulfide oxidizes
So what
very
happened, when it went from fresh
You built up-
salt, all of a sudden it
You oxidize them.
became
Yeah.
methane to sulfur, and I finally said, this is a headache, and the methane is low anyway, so I just,
Right.
you know.
And this is a good slide, by the way, to show you something else I wanted to point out.
Can I ask one more question?
Sure.
Suppose
You bought me lunch.
in the summer
Yes,
and in the main bay, you have very low oxygen.
you do.
You oxygenate that. Do you get more methane?
No, you get less because, well, if you oxygenate it, what will happen is the methane will get oxidized in the aerobic layer. So you only get methane escaping if you have run out of sulfate and if you have fairly small aerobic layers. Under both of those conditions, there's no place else for it to go. It can't oxidize. Carbon diagenesis has to go somewhere, right? So where is it going?
I've looked at the fluxes in the model, and
Yeah.
in fact, what you just said is what happens in the model.
Good.
So for for the model between the Bay Bridge and Smith Point, if you oxygenate that bottom, the methane flux actually goes down.
Yeah, that's exactly what should happen. The aerobic layer gets larger. Maybe this isn't the place to show you this. But I do want you to notice something. You see the ammonia fluxes vary from 50 to a couple of hundred? You see the SODs vary from 1 to 3? SODs are remarkably constant. You'll see even in the winter, there's SOD. And yet, diagenesis is shut off. Remember, most of the stuff in sediments is G2. If there's no more production of algae, all you're seeing is mineralization of G2. Once the temperature drops, that's it. And yet you're seeing SOD. But not ammonia flux. That was a puzzle we had to face for quite a while. I'll show you time courses and you'll see it quite clearly. But I'll tell you what it is. It's the oxidation of iron sulfide. You build up iron sulfide through the summer, that's a sink. You're storing a lot of oxygen equivalents that have to be oxidized. And in the winter, that isn't very temperature sensitive. That's a chemical oxidation. So iron sulfide continues to be oxidized, brought up into the aerobic layer by particle mixing, and then produces oxygen. There's no equivalent storage for ammonia. As a consequence, once diagenesis shuts off, the ammonia flux shuts off. That's why SOD is so constant. One of the odd things when we were early on in the game, we'd go out and measure SODs. You remember? 1, 2, 0.7, 1.5. Never got anything. Measure ammonia fluxes, they're all over the place. That's why. Isn't that interesting? Almost there, almost at the end. These are the 10 stations that Kemp and Boynton and Kemp collected data for, I don't know, 2 years that we threw away. I think 3 or 4 years we used. And here's what it looks like. So here's a plot of ammonia, SOD, silica flux, and phosphorus. Still pond doesn't have, it's aerobic year-round. You see the ammonia fluxes are down to nothing in the winter. You see the SODs are, you see that?